Okay, so today's talk would be on data assimilation in chaotic systems using deep reinforcement learning. And thank you very much for Eric and Raoul for inviting me for this talk. This talk is basically, this work couldn't have happened without my great collaborators from CAUST, Naila Raboudi, and my advisors Omar and Ibrahim, and from Texas A&M and Cambridge, Professor Idris Titi. Now, in nowadays, we have large streams of data that are incoming. And we're trying to figure out how to use this data in order to improve our model forecasts, which generally are coming from expensive, computation expensive numerical models that are imperfect due to some kind of parameterization. And the data that we usually obtain from satellites or from in situ measurements or from any type of model data, it's usually noisy, and we usually cannot observe all of the system states. So state estimation becomes a very essential tool to describe a dynamical system. And generally, we were focusing on regional state estimation, which is the effective use of how to integrate or combine outputs from dynamical models and from incoming observations in order to estimate the state of a chaotic or a dynamic system. And to do so, there are two main approaches, which are downscaling and data assimilation. And in this talk, I'll be focusing mostly on the data assimilation part, in which we have a numerical model that is running, we have observations that are incoming, and we're trying to forecast or to try to improve the state of the system in order to improve our forecast skill. And data assimilation is generally can be defined as a branch of mathematics, which tries to make this combination in an optimal approach, following some kind of optimality. And this can be done in one of two ways, most generally, either variational techniques in which we're trying to solve an optimization algorithm in order to fit a model trajectory with whatever data that we observed, or sequential data assimilation in which, as time progresses and as our model is running, we have some incoming data and we're trying to update the state each time we have data or new data, the data incoming. So the challenges generally with state estimation is the presence of uncertainties or model complexities. And in this talk, we're going to focus on uncertainties primarily, in which uncertainties can be coming from either the data acquisition part of things or the numerical model side. And in data acquisition, these uncertainties can be coming from noise in the measurement devices, or from the way that we are collecting the data. So basically, our tools are not perfect. We have lots of uncertainties due to how we acquire data. It could be human error can also be involved aside from the tools that we're using. On the other side of things, numerical models also have imperfect parameterizations, as we know that all models are imperfect. We can't have a perfect model that perfectly describes a chaotic system or a system or a real system, and this is why weather forecasts usually drift off quite quickly. In addition, we also have some kind of numerical approximations in our discretization, which causes some additional errors, especially when you're running integrating a system long in time. And here we look at artificial intelligence as a potential solution that might help us in learning new perspectives to state estimation, that basically we can use tools that are developed in AI and merge them with tools that are used in data assimilation in a hybrid approach that will help us better improve our data assimilation tools. And generally, the reason why we follow this kind of approach is that we're interested primarily in chaotic systems because they're all around us. They're in the weather forecast systems, they're in the ocean climate, they're in the finance systems, they're everywhere around us. And generally, these chaotic systems are dynamical systems that are deterministic in their nature. You have a deterministic PDE or ODE. But these systems are very sensitive to small perturbations, whether in the initial conditions or in the forcing or you name it. that once you start your system with a slightly perturbed initial conditions or forcing or boundary conditions or whatever, then your two systems will drift apart in a way that Lyapunov and Lyapunov's exponent would describe. And this is why to study chaotic systems, we usually follow an ensemble-based approach in which we start from an ensemble, a finite number of realizations of different initial conditions or different forcings or different boundary conditions. And we run all of these using the model, a la Monte Carlo, one by one, in order to get a probabilistic representation of the solution at the time where we're interested or where the forecast would end. And then instead of analyzing a single unique solution trajectory, we analyze the distribution of the predictions. So now we have a probabilistic approach to analyze our results. And this brings us to the Kalman filter, which is one of the most adopted data assimilation approaches. It's a sequential data assimilation approach in which we run our model starting from some kind of statistics about the forecast, which is our prior guess. Then once we have new observations, given their statistics and whatever, we can update our forecast to give us the analysis. And we like the ENKF because generally it's very rigorous. It has lots of theory backing it up. So you know exactly what you're doing. And it has a very simple update formula, which is the linear update equation. The problems with the ENKF is that basically it relies on Gaussian observational data. So whenever you drift from the Gaussianity assumption, it usually fails. It also works best with weakly nonlinear models, and once you go with very highly nonlinear chaotic systems, it starts to drift off. It also usually requires large ensembles in order to have good representations of the uncertainties or the covariances in order to perform a better update. And this is why we're trying to improve upon it by adopting some kind of method based on reinforcement learning. And reinforcement learning is a branch of AI in which instead of training a neural network that goes from output to input directly, the AI system basically learns how to interact with an environment or your system in order to make better decisions. So basically now our predictions are a decision of how to interact with the environment in order or how to perform a correction to the environment in order to obtain some kind of reward which tells our agent how well it's performing in this environment. And this reward is basically our best estimate of basically it assesses how well the agent is performing by interacting with the environment. And the question becomes, can we formulate the deep reinforcement learning algorithm or the idea into nonlinear data assimilation? And the idea here is that we have to understand first how reinforcement learning is different from other deep learning algorithms. And the main difference is that with supervised learning, we're training within a data set that's labeled. So we have all of the labels such that once we give a new input that is similar to the distribution of the training data set, it should be able to give an output which is similar to what it previously have seen. Whereas when we go to unsupervised learning, we remove all of the labels. So the data that we have in the training set doesn't have the cat label, but in the future, whenever we have a new image that is similar to the data set, the images in the data set, it will give us a prediction. Now, the problem with both of these methods is that in some sense, you're restricted to this is your input, this is the output that you get, and you're learning a mapping between the input and the output. Reinforcement learning comes mostly from control theory, and it has been around since the 60s, where you're learning how to interact with an environment or which step to take next in order to improve the overall reward over the long term. And by making decisions and interacting with the environment, it has been shown that you can generalize better to unseen scenarios because instead of learning a mapping between input and output, you're learning that at every single step of on the way, you're learning how to interact with the environment. So, for example, in the case shown in the figure, it's basically the cat is learning how to go to the red flag without going into the holes. And so, in some sense, it will learn that going left or going upwards is better than going diagonal. And reinforcement learning works on basically falls on four main pillars, which are policy, reward, value, and whether it does exploration or not. Policy basically is the idea of how the reinforcement learning agent has to interact with an environment to map the given state or what it observes into the action that it has to take in order to interact with the environment. Reward is basically the feedback that the agent gets from the environment, telling it how well it's performing in the environment based on some optimality criterion that we provide. Value is an estimate of how good a given state. So if you're standing at this block right now, how good or beneficial is your state into the future to collect higher rewards. So basically, it looks into the future and estimates how good staying at this position or taking a current action is compared to doing something else. And finally, exploration, in which when we're training the policy, we'd like to have some stochasticity in training in the sense that we would like to explore new actions that are potentially more beneficial or more rewarding in comparison to exploiting known actions that we know give a suitable enough reward. It might not be the best reward, but it's good enough. And the question of whether we explore or exploit is definitely a research question in the sense that we really don't know, and it depends from one case on it depends on the case. There are several deep reinforcement learning algorithms that people adopt, which are either model free, in which we don't have a model of the environment, we don't know how to interact, and this would be the general chaotic system case, because we have the environment, we know the PDEs, but we don't have a model for the reinforcement learning agent to interact with. Whereas in chess, for example, we have an exact set of rules of how to move the pieces and how turns go, and this is what we call as model-based reinforcement learning. And for model free, I'm going to focus on the PPO algorithm or proximal policy algorithm, whereas there are a plethora of different algorithms that could be adopted. And again, this is what worked for us. It could others can try different algorithms and show different results that might be better or worse. We did try the A2C, which is an actor-critic based approach, but again, we preferred the proximal policy optimization for reasons that I will show in a few. And basically, the PPO algorithm was proposed in 2017 by Shulman et al. From DeepMinds. And the idea here is that we're training two agents. We train an actor, which interacts with the environment, and the critic, which tells the actor in some sense how basically it estimates how good a current state is into the future. So it estimates the reward that you're getting by being at a certain state. And here we parameterize each of these actor and critic. The agents are parameterized as neural networks, and we parameterize them as a very simple MLP or densely connected neural network. But this is not a restriction. You can go with any neural network architecture that you see fit. So if your data, let's say if you're observing images, you might go with a convolution neural network. Whereas if you're looking at time series, you might look at a recurrent neural network. And again, the sky is the limit here. It's a design choice. And the objective to train our neural network, the objective to train these actor and critic networks is to train them jointly with one loss function where you want to maximize the reward but minimize the error in the prediction and in the predicted and actual rewards. And first we need to define what a reward is. The reward is defined as a discounted reward in which we have a geometric series where gamma is between 0 and 1 to make this sequence or the series convergent. We also define an advantage, and here advantage could be positive or negative in the sense that if the action value, so the value of taking a certain action given a certain state is higher than the value average, which is the integral over all actions, the value of a state or state value, then the advantage is positive, otherwise it's negative. So in some sense, the advantage tells you how advantageous or disadvantageous an action is at a given state in compared to the average or the integral over all actions being at that state. And putting all of these elements together, we can see that the loss function for training the reinforcement learning agent and critic basically requires L-clip and L-value function, which are optimized jointly at the same time, in which L-clip is the clip advantage, which is the expected value or the average between the advantage that we get with some penalty term, or a clip term where we have 1 minus epsilon and 1 plus epsilon in order to make sure that our changes in training are not huge. Usually epsilon is around 10 to 20%, in the sense that we would clip our advantages in the sense that the policy or RT doesn't change by a huge amount. So basically changes in the policy with the new theta compared to the old theta shouldn't be huge. And this is why we use a clipped loss function. Then, in other terms, to simplify the idea of why we need this, it's basically it requires maximizing the advantage, but we don't want to change the policy by much. And this is why we penalize changes in the policy. On the other end, we try to maximize the value function loss, in which our estimate, where the critic estimates the value of a current state, and again, the state value function, it is the integral over all actions for being at a given state, should be as close enough as the actual value that you get after taking some kind of actions. So in some sense, the value function trains the critic to give you the best estimate of the state such that your rewards are you can have the best estimate of the rewards into the future, whereas the clip function will train the agent to take the best action that maximizes the reward. And to test our algorithm, we first start with the Lorenz 63 system, which is the simplest system and considered as the benchmark for most of the data assimilation algorithms. And the idea here is that we're trying to assimilate noisy observations without knowing anything about the distribution of the data, and without having any additional knowledge about what's going on. And as we'll see from the results later on, it's quite different in the assumptions that we're taking for adopting the algorithm. And the Lorenz 63 system is the system of ODEs, the coupled ODEs. And we know that for these parameters, we get the butterfly attractor. So reinforcement, what we propose is that basically, given a cycle, an assimilation cycle, starting from the red triangle, we can run our dynamical system. These are the ODEs, or your forecast in some sense. You collect the state at every model step that you choose, whatever you can afford, till you get an observation. At the observation time step, you concatenate your vector of states and derivatives with the innovation term, and you use that as input to the policy function. Since the policy function is a stochastic function, you can sample it as many times as you'd like to get an ensemble of corrections, and these are the data assimilation corrections that you can obtain. If you want to run the best correction, then you take the maximum a posteriori, and you can run your forecast with the sample with the correction with the highest probability. Otherwise, you can sample as much as you'd like, and you'll obtain a distribution. And this is in fact what we do to show our results. In the sense, we run Monte Carlo sampling in order to get an ensemble of different analyses, XA. This is not ideal, especially in high dimensional systems, as we will see. However, this is a first start to introduce reinforcement learning to data assimilation. And of course, there will be many approaches to improve upon what we present here. So to show some results, the first case is for the sensitivity to noise level, in which we're observing all of the states and assimilating the Lorenz 63 system once every 50 time steps. So we run the model every 50 time steps, we get an observation, we perturb this observation with Gaussian noise with standard deviations of 1, 2, and 3, and then we try running the assimilation. What we see from the results is that with a single realization, so you're only seeing one trajectory of the solution, the reinforcement learning agent without any additional information does the worst in comparison to the EnKF with 50 realizations. But when we sample 50 corrections from the reinforcement learning agent, then we're able and average the solution, we're able to do better than the EnKF with 50 realizations. And this is not based on a single simulation, but rather on 50 realizations, 50 repetitions of the experiment. And this is what you see with the shaded color, which is the plus minus one standard deviation of the error based on 50 repetitions of the experiment. Now, in order to better analyze what's going on, we look at the corrections and the distributions and how they change over time. And what we see here in the figure is that upon performing some corrections, the distribution of from the ENKF is a bit more narrow and it's more Gaussian, whereas for the RL it could be skewed, as we can see from the first case, and it's wider, especially in terms of the corrections, which means that the RL is a bit less conservative in its corrections and pushes some of the samples to go outside of the mean value. And this is cool to see because essentially what we're trying to say is that the RL is able to give you corrections that push you away from Gaussianity to give you bimodal or non-Gaussian distributions in the analysis. And this is somewhat breaks the loop of staying in the Gaussian assumption and staying in the linear model. Now, to test this a bit more, we look at the assimilation frequency, in which now we're assimilating all of the states with standard Gaussian noise perturbing the observations, but now we're assimilating the data once every 5 time steps, 50 time steps, and 100 time steps. And in some sense, you can think of this as the most linear case, and this is the most highly nonlinear case. And we can see the same conclusion as before, is that basically RL1 cannot assimilate the system, which makes sense since we're only looking at one trajectory of the solution, and this trajectory is also perturbed. It's still doing reasonably well in all of the cases in terms of RMSE. However, it doesn't outperform the EnKF, which performs really well, which is expected since we're in the Gaussian, we're respecting all of the assumptions required by the algorithm. And when we go with RL50 and assimilate 50 different realizations of the correction and averages the resulting solution, we can see that we can outperform the EnKF in all cases. In the first linear case, we perform comparably well, so it doesn't really make sense to compare, but still, you're able to do the same without inverting a covariance matrix. So there's still some benefit to the algorithm. Now when we go to the non-Gaussian case and assimilate data of different noise models, we can see that the RL, whether RL1 or RL50, can outperform the EnKF in the uniform noise case and the log normal case. Whereas for the Gaussian case, this is indeed what we've seen earlier, is that RL50 can outperform the EnKF, whereas RL1 cannot. Finally, we look at partial observations, and in this case, instead of assimilating all of the variables or all of the states, we're assimilating a combination of different states. So we either assimilate the x variable by itself or the x state. So basically, we have observations of x, or we have observations of x and y, or we have observations of x and z. And we have observations once every 50 time steps, where the observation is perturbed with Gaussian noise, with standard Gaussian noise. So basically, our standard deviation is 1. And here we can see that when we're observing X by itself, the RL50 actually outperforms the EnKF by a margin, which was comparable in the difference between the EnKF and RL1 in the previous cases. RL1 still does the worst, but again, it's expected since it's only seeing one realization of the state and not seeing an ensemble of states. Finally, the EnKF does worse than the RL50, but better than RL1, which is expected. And again, since we're in the Gaussian regime, we're still able to assimilate these noisy observations in a reasonable enough way that basically we're happy with what we see. Next, we look at the higher dimensional system, in which we look at the Lorenz 96 system, given by the ODE here, where we have an interaction between the states at the beginning and the end. So basically, it's like a roll, and the system is basically highly chaotic when your forcing goes beyond 8, or yeah, beyond 8. And then we look at different cases, and here I'm starting with the case of the noise distribution, in which we've seen before that the NKF cannot assimilate non-Gaussian noisy observations. We try to see whether it's the same with highly nonlinear models, or whether the RL would fail. And here we can see the results are a bit interesting. So we compare the ENKF in the case where we have covariance localization and inflation and localization, and in the case when we take the plain vanilla ENKF, and compare those to the RL with a single agent versus RL with 50 realizations or 50 corrections. And for the case of Gaussian noise, we can see that the plain vanilla ENKF fails. It has the highest RMSE. The ENKF with covariance, inflation, and localization does the best, which is expected since these bells and whistles are what we need, especially in the case of the Lorenz 96, given its structure. Whereas the RL 1 and 50 perform okay-ish. I wouldn't say they perform the best. First, and this can be explained due to a few reasons, and again, since we're trying to first propose the new method, we didn't implement anything such as covariance inflation or localization. We don't have any estimate of the uncertainties going on in the system. So it's basically, even when you change the noise level, our RL agent is not informed by this change, and it still follows the same assimilation strategy. So it's not able so it's basically, it tries to learn your R inverse matrix by interacting with the environment. And this is why our errors are a bit larger than the optimal ENKF. But again, this gives us room for improvement of the next DARL algorithm. And in the case when we go to log normal or uniform noise models, we can see that the ENKF fails, so we didn't plot it on this figure, whereas the RL1 and RL50 somewhat have a much better performance. They show comparable performance to the case of the Gaussian noise, except for the case of uniform noise, where our errors are way smaller. But again, the distribution plays a big role. And to conclude, basically, we show that RL has very good applications to data assimilation, in the sense that now we have no, nonlinear correction schemes. Uh, it's adaptive to new cases, such that once you train it for one case, you're learning how to interact with the system. You're no longer learning a mapping from an input space to an output space. So it helps by generalizing better to new conditions, because again, it's state adaptive. And we don't use any restrictive assumptions, in the sense that we don't know how large or how small the noise level is. We don't know whether the noise is Gaussian, log normal, uniform, or whatever. We're training the agent by interacting with the environment, and later on basically throwing this agent into the real world and trying to assimilate noisy data. Now, this is, of course, a first step into this direction. This is the only work that does reinforcement learning for data assimilation. So it means that our algorithm needs a lot more work. So it's very expensive. We have to find some more efficient strategies to go to very high dimensional problems, such as weather or weather, atmosphere, or ocean. And there's little to practically no theoretical work on how reinforcement learning can be connected with data assimilation, especially whether there's a connection to Bayesian filtering, for example, especially that if you think about it, what we're doing is an optimal control strategy that is parameterized by a neural network. And if you consider this as a black box, as a surrogate model, or whatever reduced order model that you might like, then it could be that there is a connection with the EnKF, but again, no one looked at this before. If you're interested in this work, I also left a QR code of the paper. And with this, I thank you.
Thank you very much, Abed. It was a very nice talk.